Today we are going to discuss the next topic is about the mm, Fresnel biprism, Newton ring, and Michelson interferometer. So in the morning we have discussed there are two methods for interference. One is by division of wavefront, another is by division of amplitude. Division of wavefront means sources are split up into two parts and they are adjusted in such a way that the coherence is being produced. They produce coherence beam and the pattern is being observed. Second is the light is being emitted from the source and divided up into two different parts, either reflected or transmitted, and then they are allowed to interfere and then the pattern is being observed. So that means interference can be observed by two different methods and different techniques are being there. Each technique has their own advantage and own disadvantage. So we are going to do the application of division by wavefront. One of the application was Young's double slit experiment, and then this one is Fresnel biprism. Then third is Lloyd prism. So according to syllabus, we are going to discuss Fresnel biprism. So we can discuss this in two different parts. So you have as shown in the diagrams. So we have seen there is a prism biprism. Basically, prisms are of different category. ABC, that is an equilateral prism where each angle is of 60 degree. Now then there is another prism that is called as right angled prism where one angle is 90 and other are 45. So it is a special kind of prism where one angle is 179 degree and other is of half degree and other is of half degree. So that means it is an isosceles prism. Two different angles are equal and one angle is very high angle. So here when the single source of light is used and then the light is going to emit out and then reflected beam are formed, so that the virtual sources are being formed at S1 as S2, and then the interference pattern is formed on the screen where at the center maximum brightness is there and then alternate dark and bright fringes are going to be formed. So let us say A is the distance between the prism and this one, and then B is the distance between the prism and the screen. First is between the sources and the prism, then the prism and the screen. Let us say capital D is equal to A plus B, which is the total distance between A plus B. So we can find out the wavelength by using this relation. Beta is equal to so lambda is equal to beta into 2a mu minus 1 into A upon A plus B, because it is a formula lambda into D upon D, and lambda into D upon D is there. If the refractive index is also being there, so we can find out the value of D can be written as so this is basically beta is equal to lambda D upon small d, or lambda is equal to beta small d upon capital D. So capital D we know it is equal to A plus B, small d we can read it equal to 2a minus mu 1 into A. So that's why this relation we used to get it out. So that is one method of doing it. Now if this is without using any lenses. Now we can use lenses also inserted between them. Let us say these inserted two lenses are being inserted between them, and then what happens, there will be two different position of lenses, one is L1 and another is L2, and when the sharp images of coherent source will be observed in the eyepiece, the separation of the images in the two positions are measured. Let there be D1 and D2. So then what we can do is we can using the formula of magnification, that is size of image upon size of object, D is equal to D1 upon D, and then for second u upon v is equal to d2 upon d. Now when you take the product of these two equations, you will get d is equal to root of d1 d2. So that means the distance is coming, instead of 2d into mu minus 1, here it will be come out to be d1 into d2. So again beta is equal to lambda is equal to beta d upon d, or sorry beta lambda is equal to same relation lambda d. So we not beta is equal to 2 lambda d upon d, lambda d upon d. So we can find out lambda is equal to beta d upon capital D. So beta small d upon capital D, small d is equal to root of d1 d2. So capital D is equal to a plus b. So that means this is the second formula for using the Fresnel biprism. That's how the interference pattern is going to be get observed. The distances can be get observed between the two sources, coherent sources, which can produce a perfect interference on the screen. Now we can use the second method where the division by amplitude, that is Newton ring method, and then we will discuss about the Michelson interferometer. the diagram for Newton's ring method, where we have got a convex lens of if the convex surface of a planar convex lens of large focal length is placed on the plane glass plate. This is a glass plate. Here the convex lens means the thickness of the air film is 0 at the point of contact O. Here there is no thickness of air, while there is a certain amount of air is there. The thickness of air film is 0 at this point and increases as we move away from point O. So this thickness of air goes on increasing at this one. If we allow monochromatic light to be incident from the upper part, that is lambda, to fall on the surface of the lens, then the light reflected from the surface AOB. So that means this point of surface will be there. Let us say we call this AOB. So this point of surface will be get reflected back, interfere with the light reflected from surface POQ, that is from POQ. So that means this light and this light, both of them are get interfere at this point. For normal incidence, the condition for maximum will be equal to 2D is equal to m plus 1 by 2 into lambda. That is the condition for maximum. Now for minima, 2D should be equal to m into lambda. Now the value of D, how to determine it out? So we know that this is capital R, this is under root of R square minus R square, this is small r and small, this is the D, which is a gap between the plate and this one here. Now we can find D is equal to R minus under root of R square minus small r square. So we can take it out common, R common, under root of 1 minus R square by capital R square power 1 by 2. So or we can write it as R minus R into 1 minus R square by 2R square. So that means 1 minus something, it will be very small, and when you take it out, approximate value will be equal to R square by 2R. So that will be equal to D. So that means the value of R, will be can be find out from this relation. R square is equal to 2R small d, or small r is equal to under root of 2R capital D under root. So this is the value which we are going to observe. Now for the dark range, what we will do, this is for dark condition for darkness, this is for brightness. Now for dark range, we will substitute the value of D from here into this equation. So this value of R is equal to under root of this one is 2R into small d is equal to m lambda upon 2. So that will be equal to under root of R m into lambda. So that will where m could be equal to 0, 1, 2, 3. So this is equal to diameter of the mth dark ring. So that means the radius of the diameter, radius of mth dark range can be find out. Dark range can be find. This one dark ring can be found basically when the interference pattern is formed. So there are this kind of pattern will be formed, while in case of previous method only slits are being observed, which is being shown on the screen, that is dark and bright fringes are there. But here in this case of circular rings are being formed, dark, bright, like that. Alternate bright and dark fringes are going to be get observed from this method. So this method is one of the useful method for measuring the interference pattern, and by measuring the the diameters, we can find out the size of the ring. For different rings, we can able to find it out. For bright ring, we can find out D is equal to m plus 1 by 2 into lambda upon 2. So we can put this value over here. So that means R is equal to root of 2R, D is m plus 1 by 2 into lambda by 2. So this will be cancelled. So that means equal to and that value comes out to be equal to R lambda into m plus 1 by 2. So that means for bright fringes. This is for dark fringe that you had observed it out. Now that is the relation for this one. Now if you take the m plus mth ring and the square of distance, so we can find out d m plus p whole square minus d m square, that will be equal to 4p lambda into r, or lambda we can able to find it out as d m plus p whole square minus d m square upon 4pr. So that is the lambda wavelength of the light can be measured from using this experiment. So this is one of the method for measuring the interference pattern, that is division of amplitude is being there. Now, this is the incident of Michelson interferometer, where again the difference of amplitude is going to taken into account. It consists of a source, a lens, two different glass plates, and then two different mirrors are being there. This is a moving mirror which can be adjusted to get the interference pattern over the screen. So here, once the light comes out to be, it's split it up into two parts. So this is a adjust light which compensate the time travel to compensate used for the compensation of the time to be taken by the light to travel from this to this, as well, because according to relativity, light will take more time here as compared to this one. So to adjust that time, so this plate has been adjusted there too. When the beam is being selected over here, we can get it here. Now to observe the interference, and this beam will go here, reflected back, and then one beam here reflected back, both the beams are allowed to interfere, and the interference pattern is observed on the screen. Now as we shift the mirror, so let us say that the width is shifted by x, so the beam will travel go and come, so that means the beam has to travel the distance of 2x. So to observe the maximum, so n lambda will be there, lambda is equal to 2x by n. So that means by shifting this one and by counting the number of fringes, we can find out the wavelength of the beam, whatever the going to be observed. So that is one of the method and one of the application of this one, that is to determine the wavelength of the source, wavelength of light. That is one of the application. Now second, and the fractional change in wavelength can also be measured. Fractional change in sodium light can be observed. Now here what happens, let x1 is the displacement of the mirror m2 for two consecutive position of the illumination. Let us say 2x1 is equal to n1 into lambda 2, and when the minimum corresponding to lambda 2 falls on the maximum corresponding to lambda 1. So that means this is the condition of minima, and that 2x1 is also equal to n plus 1 by 2 into lambda 1. Now we can compare these two equations, that means 2x1 upon 2x1 upon lambda 1, 2x1 upon lambda 2, lambda 2 is equal to minus 2x upon let us say lambda 1 upon lambda 2, that will be equal to half after solving this, because both of them equal to n1, so we can put this value and get the value of this equation. Now this equation further be simplified. If the mirror is moved, m2 is moved through a distance x2, this mirror is moved to distance x2, we can find the sample, that is a value for equation for x1 in the form of x1. Let us say this beam is shifted to x2, so again we can get 2x2 upon lambda 1 minus 2x2 upon lambda 2, that is equal to 1. So once you solve this equation, so you will get lambda 2 minus lambda 1 is equal to delta lambda, which is equal to lambda square by 2x2. So that means so this change in wavelength is measured by lambda square upon 2 lambda 2x2. That means whatever the width is being shifted, so according to that we are going to measure the change in the wavelength. So these were all about the different part of the interference which has been observed by division of amplitude or division of the this one. Thank you.